Okay. So now we are going to start with metal semiconductor junction. So in contrast to what we have seen metal oxide semiconductor junction, now we are going to remove that oxide layer and we are going to have only metal semiconductor junction. So now in the recent days, that removing an oxide layer is going to give us a very good in terms of performance parameters. So what we have done, we have removed the oxide layer and we are going to create devices based on only two layers. Initially, we use metal layer, oxide layer, and semiconductor layer, right? Now, after removing that oxide layer, I'm going to have only metal and semiconductor layer. So depending on various parameters like doping concentration, how much acceptor impurities I'm going to add, how much donor impurities I'm going to add, what material I'm going to use, whether I'm going to use silicon or germanium, or I'm going to use group 3, group 5 materials, and what interface I'm going to have, whether it is metal oxide semiconductor or it is metal semiconductor junction. So you can make the device to work either as a ohmic contact or as a Schottky barrier. So the main application of metal semiconductor junction is the application is going to be Schottky barrier diode. So this leads to a new type of diode called as Schottky barrier diode. So Schottky barrier diode is going to use a metal semiconductor junction. So before understanding Schottky barrier diode, we need to clearly know what is the working of a metal semiconductor junction, or how will the construction be, and what all the parameters we have to consider when we start understanding the metal semiconductor junction. So as the name indicates, metal semiconductor junction means you're going to have a metal layer which is going to be in direct contact with the semiconductor layer. So in between, the oxide layer is going to be completely eliminated. So I'm going to have a metal layer which is going to touch your semiconductor layer. Okay, and whenever you're going to have this type of combination, the active interface, you are going to have a junction. So definitely when you join two materials, definitely you will have a junction. Okay, so that junction is going to act like an anode, and the junction is going to be the interface between the metal and the semiconductor. So junction is going to act like an anode. Okay, so this is the basic thing. As you know, the diagram you can see. So you are going to have a metal semiconductor junction. See here. So you have a portion of metal here. The shaded portion, what I'm showing you is the semiconductor, and this portion is going to be the metal. This is your metal, and this is your semiconductor. And definitely, whenever you are going to join them, whenever you are going to form a metal semiconductor junction, you are going to have a depletion region. So this depletion region is given here in the dotted. This region is common to both the metal and the semiconductor region. And this metal side of the semiconductor diode will act like an anode, and the N type will act like a cathode. So N type, you have the ohmic contact that is going to act like your cathode, and in the metal side, I'm going to have an anode, and you know anode is positively charged and cathode is negatively charged. The current is going to flow from cathode to anode. So see here the current direction I is given, which is going to flow from cathode to anode, or I can say the current is going to come out of your battery. So the other interface between the semiconductor and the metal, it is going to act like an cathode, is an ohmic contact, and there is no potential drop at this junction. Okay, two interfaces is there. One side is the metal side of the device, and one is the semiconductor side of the device. So one interface we have seen, the active junction is the interface with the metal which acts like an anode. So this is one junction, and the second junction is on the other side, which is going to be the cathode, which is going to be an ohmic contact. So anyway, if you want to take a wire, you have to give a contact, metallic contact, right? So here also you will have a small metallic contact here, and this contact you have no potential drop. So the potential drop is going to be zero, which means that keeping this metal layer will not affect the current flow inside your device. So, okay, this is the construction of a metal semiconductor junction. And before going into the theory of metal semiconductor junction, we need to understand where the energy band of the semiconductor is going to lie, whether it is going to be dependent on the metal layer or the semiconductor layer. So for that, we are going to slowly go into the energy band diagram of the metal semiconductor junctions. So this is the energy band of metal semiconductor junctions. So you see here, this is the energy band of metal. Where this is the individual energy band of metal. This is the individual energy band of semiconductor. So you see here, we are going to have an N-type semiconductor. You know, in N-type, electrons are going to be the majority carriers, and in N-type, we are going to dope with donor impurity. Correct. So when you're going to dope with donor impurity, the Fermi level will be lying very much close to your conduction band. So that is here, and the intrinsic level will always lie exactly at the middle, and you have a valence band exactly at the bottom. The energy difference between valence band and conduction band is called as forbidden energy gap, EG. Fermi level is close to conduction band. Intrinsic level is exactly the middle of your conduction band and valence band. Okay, but in metal layer, you don't have conduction band and valence band because they're overlapping, and just by supply, the free electrons are available directly to flow from the uh, in the conduction band. So you need not supply any energy for the electrons to flow inside the metal to get your current. So these two diagrams are individually given when I'm going to have a metal separately and when I'm going to have a semiconductor separately. Whenever I'm going to have a metal semiconductor junction, when you join this metal and semiconductor junction, then this energy band diagram will fit in here. And you can see that the Fermi level of metal will be slightly above the valence band of your semiconductor layer. And the final the energy band diagram is simply going into this metallic structure. That is what is the diagram shown here. So these two diagrams are given separately, and this diagram is given when they are going to make a metal semiconductor junction. And the corresponding energy diagram, energy notations are going to remain the same. So the understanding of this metal semiconductor junction is given in the next